Alright, so as promised, I said I would create at least a video or two about how to solve for series and parallel circuits given a set of resistors and the total voltage. Usually these will always be given to you, only because if you don't have it, it makes it slightly more cumbersome, and we don't quite have time for that. Remember, each test question is about 2 minutes a question. This is about 2 minutes if they ask you for a single value, but never mind that. So first things first, we need to remember, identify the type of circuit you have. We have a battery, we have 3 resistors, and they're all on one loop. Battery, 3 resistors, 1 loop, that's only one type of circuit in a series. So because that's a series circuit, we need to check some things. We need to check our rules. So for a series circuit, please remember that your voltage is going to be the addition of each individual voltage drop. Voltage drops are what you'll find across each resistor. And so the total voltage is equal to the sum of each voltage drop. So each resistor has its own voltage. Add them all up, you get your total. Your resistance in a series circuit, same thing like your voltage, adds up. Yeah, it just adds up. So your voltage and resistance adds up all because it's on one loop. However, your current is constant. It's a terrible lie. That's better. It's like if there's only one checkout lane available, right? That one checkout lane is probably gonna have all the people in line. It's gonna take forever. You can't skip the line, you can't jump in line, so you have to stay at the same pace as everybody else. So, with those rules in play, it's one more rule. It's the power rule. Not the one from calculus, but power is just going to be the addition of power expended from each resistor. Again, you find the power for each resistor, add them all up, and you get your total. So, since everything's more or less in place, all you have to do is solve. Now, let's see. We know that resistance adds up. So we have 3 plus 9 plus 6. We have 3, 9, and 6. What is that? 18. We did a total of 18 ohms of resistance. We have 18 ohms of resistance. That's because we were adding up each resistor, and we're done. So now that we have that in place, we have our total resistance, we have our total voltage. We don't know the current quite yet, but we can solve for it if we have the voltage over the resistance. Again, voltage over resistance gets you your current. All we have to do is figure out what's 12 divided by 18. Divided by 18. 0.67. And of course, the units for current are amps or amperes. All right, so we found the total resistance, we found the total current, and because we're dealing with a series, you can't jump in line. All that current must stay the same. So 0.67 amps all around. All right, that makes it a little more convenient for us because we've dealt with our resistance, we've dealt with the current, now we're gonna go deal with our voltage. We can't quite do the rule for voltage. We need to revert back to Ohm's law so that we can use what we know to solve for what we don't know. Again, we know the resistance, we know the current, we're solving for voltage. Remember, voltage should be current times resistance. All right, well, let's do some math. 3 times 0, 0.67 to volts. We're at 6.03 volts. Last but not least, 6. Oh, I'm sorry, I already did 6. My brain is broken. Let's do it better. 3 times 0.67 should be. There we go. That's fine. This is not fine. Now, if you were to add these up, you'll notice that it's a bit more than 12. You probably, 12.07. That's usually just a rounding error. It's fine. If you want, you could just round up enough to only get your main values, but I like to be a bit more thorough. Last step is finding our power. You've probably forgotten how to find it, but it's okay. Power is just current times voltage. And we have both of those now, so we should be fine. Let's see. We got 2.0. 2 times 0.67. 1.35. 6.03, 4.04, and last but not least, 402, 2.69. Let's try a big number. 0.67. We end up with 804. Yeah, you know, with some weird numbers, but we're all done. Again, take your time. Typically, there's a slight pattern to this. You want to more or less go in, not necessarily these steps that you can go. The steps I would organize is first, for a series circuit, find your total current. That way you can run all the way through. After that, once you have all your currents, you have all your resistances, find your voltage and find your power. So you really want to work kind of left to right. It is different in your parallel circuit because different rules apply. But if you want, of course, you can kind of follow this pattern, but it's really up to you. So, first one done. Go back if you need. All right, so part 2 is just going back and solving for a parallel circuit. So again, step 1, recognize you have a parallel circuit, and now there are different rules applied in the situation. Got a parallel circuit. All right, so parallel rules. We need to keep in mind that your voltage is constant, so your total voltage will equal all the voltage drops for each resistor. Again, voltage is constant. All right, next rule. We have to remember our current is going to be added up. So the current for each branch, the current for each resistor, is probably going to be different. And even if it's not different, add it up to get the total. Oh. Guess my brain is thinking series. Swap those out. That's better. And of course, there's the resistance rule. And so for resistance, it is going to be slightly challenging to solve it. I like to use kind of a backwards approach, but you can use this equation to get to the point. Same process, gets you the same results, just a slightly different approach. For resistance, to get the total, you're going to have to invert every resistor. So you're going to invert each value for the resistors, add them together. So invert the value of each resistor, add them all together, and then invert that value. So one more time. To find total resistance, you need to invert the value of each resistor, add them together, and then invert it one more time. Okay? And power is going to be the same as the previous slide, the previous question. So you can backtrack to that one if you want. So let's go and start solving. I will write out what the resistance is going to look like. That way we have something to backtrack to. Make sure you have this down and pause it here so you can write it down. I'm about to erase this. 5, 4, 3, 2, 1. All right, goodbye, rules. Hopefully I remember you. All right, so we're gonna look for total resistance, even though we can definitely find some other stuff a bit easier. We are going to take 1 over 20 plus 1 over 100 plus 1 over 50 and invert that one more time. Now that least common denominator is 100. You could solve it like that if you want. I guess we can actually. 100, 5, 1 over 100, and then 2 over 100. And it was 8. And then we want to flip that one more time. 100 over 8. Again, if you have an easy least common denominator, then this one's fine. That should be what, 1 point, 1.2 something. Wow, I said 1.2, it's 12.5. Guys, I'm losing my mind. But 12.5 it is. All right, so I'm going to leave this up for a moment. Go ahead and write this out. This is the process you would take for finding the resistance in a parallel circuit. Remember, this is how you find the resistance in a parallel circuit. If you want a little cheat sheet here, or like a little workaround, typically it'll be multiple choice, right? Where you're going to be given a list of options. What is the equivalent resistance for this type of circuit? Don't be fooled. Equivalent just means total. So what is the equivalent resistance for this circuit? It'll give you a range of values. Your trick to help eliminate certain options is, remember, the total resistance in parallel. Again, the total resistance in parallel is always less than the individual resistors. So it'll always be less than R1, it'll be less than R2, less than R3. So if you have an answer choice where the answer says that, hey, it's more than 100, it's more than 50, it's more than 20, they're all wrong. The total resistance in a parallel circuit is always less than the individual resistors. Again, I would write that down if you want. All right. So now that we have that and we have the voltage, we should be able to find everything else. Oh, but there's something even easier we can do, because remember, voltage in a parallel circuit is constant. Why is it constant? Well, each one of these resistors has a direct path to the battery. If any resistor was removed, it would not matter to the rest of them. So again, voltage goes all the way up through our table because each resistor has a direct path to our battery. So let's go ahead and get this. All right, so this is actually not bad. What, 10? Good. That's just 10. Yeah, total 10 amps. Let me check that out. Shockingly easy. So, in order to get this, remember, we're using Ohm's law to figure out the actual table. We don't have to use the rules anymore. We just have to use our original idea for Ohm's law. And for current, it's just voltage divided by resistance. Again, just voltage divided by resistance. So we get 125 divided by 12.5. Yeah, you get 10. Easy. Let's do the rest. 125 divided by 50. Okay. What? Well, yeah, there. All right. 100. Last but not least. And so here's how you know you did this correctly. Remember, for current, it should all add up. Again, for current in a parallel circuit, these values should add up to your total. So let's see, 625, 125, that's not 8.5. Oh, so it's 7.5. 7.5 plus 2 is 9.5, plus another half is 10. So yeah, we're good. Fine. What's the last step? Oh, last step is power. Oh, yeah, nice things. So remember, power is just current and voltage multiplied together. We can go ahead and do that. So 625 times 125. Oof, so much power. So 781.25 watts. So next we have 125. A little bit of a step down. 156.25. And then last but not least, you got 2.5. And back up to 312.5. Well, this should all equal, what is that, 1,250? That. So, this is how we would solve for a parallel circuit. Now, if you do not want to do this process here, you have to understand and be familiar enough with the fact that voltage in a parallel circuit is constant. If you do not want to do this math, which you're gonna have to probably do anyway, understand that voltage is constant, so you can have voltage run all the way up this table, and then kind of work backwards. Because you're given the resistances, and you have the voltage, you can go back and find the current, right? That current, for each one, you add together, and then get your total resistance that way. Again, it's a bit of a way to work backwards, but it is a way you can take and not have to worry about this much math, at least in filling out the table. The power checks out, which is fine. Is there anything else we need to go over? Oh, please go back and look at the rules for both series and parallel circuits. You're gonna need them, especially when we start talking about combination circuits. So when we start talking about combination circuits, you're gonna have to be very well versed in the other two forms. If I didn't mention before, the goal here is to simplify as much as possible. What we've done, in effect, is simplify these circuits down to its bare components. Combination circuit is going to take a little bit more out of us, as it's going to take some more effort. So practice, and practice. Of course, this will not be edited. If I stumbled somewhere, it's fine. Have a great day, unless you're watching this at night, in which case, go to sleep.